Hello and welcome to this presentation related to our Applied Maths unit. Here we're going to consider past paper from Jan 2023. This is now revision week 5. Here's an overview of the contents of the paper. In this week's revision session we reviewed questions 1, questions 2 and partially outlined question 3. I would encourage you to try and complete question 3 and also attempt question 4, 5 and 7. As they contain work we've covered throughout the duration of this study. Again, full detailed work solutions are shown to each of the questions. And for your reference, here are the approximate start times related to the questions contained within the presentation, should you want to specifically review a particular solution. But please note all times are rounded to the nearest minute. So here's question 1. This relates to calculating areas and volumes associated with a small deep fat fryer. Notice to give us some reference information in the question that 1 litre is equal to 10 to the power of 6 millimeters cubed. That just helps with the later conversions. This slide is purely for reference. The conversion we're more familiar with is 1 metre cubed is equivalent to 1000 litres. In question 1 we're considering conversions to millimeters cubed. So just showed here the unity bracket that converts fluid of volume 1 litre into millimeters cubed. So we show that 1 litre is equivalent to 10 to the power of 6 millimeters cubed. As I said, this is purely for reference, and if you're interested in the use of unity brackets, there is a separate presentation on this topic. So part 1, we have to calculate the volume of the tank when filled to a depth of 60 millimeters, given the answer in terms of litres. We're given the above plan view of the deep fat fryer in figure 1b here. So as a hint, essentially we have to calculate the area of the deep fat fryer base, shown in figure 1b, and simply multiply that by the height to find the volume. Solution shown on the following slide. Question 1b, here's part 1 solution. So firstly we calculate the area, shown here. So we're going to calculate the area of the square base, this area shown here. Next we calculate 4 times the area of the rectangles. Here's the area of a rectangle. Of course there are 4 of them. 1, 2, 3, 4. And then we add to that the area of a circle, which essentially are these 4 quadrants. 1 here, 2, 3, 4. So that calculates the area of the base shown here in millimeters squared, and we calculate the volume by simply multiply the area by the length or the depth. That's a depth of 60 millimeters stated in the question. That gives a volume here in millimeters cubed, and of course we have the conversion in the question of 1 litre is equal to 10 to the 6 millimeters cubed, so the volume can be converted from millimeters cubed into litres, stated to 2 decimal places here. And that was worth 4 marks. This question 1, part 2. This time it relates to a new design of the deep fat fryer. We have a different value for length here. And in the question we're given that the depth of the oil in the tank is now 50 millimeters, and that contains 2 litres of oil. So we're given a volume effectively. We've got to calculate the value of R this time. So find this value here, the same in all the corners. The hint here is to generate an equation for volume in terms of the radius R. I'll show you the full work solution on the following slide. This is question 1, part 2. Here's the solution. Notice we initially stated the 2 litre volume in terms of millimeters cubed. That's the conversion given in the question. The depth or the length of the fryer is 50 millimeters. So a very similar approach as to part 1. It's just that this time we're going to generate an equation in which R is an unknown. I'll let you review the solution at your own pace. Essentially we'll form a quadratic equation in R, which we can solve using the quadratic formula. Value for R shown here. Obviously there are 2 solutions or 2 routes when solving a quadratic, but we ignore the negative root in this context. This is question 1, part 2 solution. It's alternative. The only thing that's different here is I've used meters instead of millimeters. So my initial volume is from 2 litres is changed to 0.002 meters cubed, and my length or my depth is 0.05 meters. As I said, just an alternative approach, probably non-preferred in this case, but the final value for the radius is exactly the same. Question 2. Again, we've covered similar kind of questions in previous revision sessions. It's involved considering a free body diagram of a mass that's in equilibrium. So we have a small object, labelled as O, shown here, has a mass of 10 kilograms, shown as 10g here. The g is gravitational acceleration, suspended by 2 inextensible cables, in other words they do not stretch, as shown in the figure 3 here. So that's the context of the problem. Question 2, I'll let you read this at your own pace. So for question 2 part 1, we've got to calculate the value of alpha, the angle, given that y is equal to 0.5. So we've got to calculate this alpha, and y is 0.5, and of course this length here is 2 meters. Full work solution shown on the following slide. So question 2 part 1, I'll let you review the solution at your own pace. Angle alpha approximately 14.5 degrees. Question 2 part 2, we've now got to calculate the value of x when y is equal to 0.5. So we've got to calculate this value, knowing this value. Solution shown on the following slide. Question 2 part 2, let you review the solution at your own pace. Here's the value of x shown here, calculated using Pythagoras' theorem. Or of course you could use basic trig. Question 2 part 3, got to prove this expression for tan theta 3 plus 2 sine alpha divided by 4 minus 2 cos alpha. More complicated question here, but try to add some hints to the diagram on the right hand side. This is the theta value here. Here's our alpha here. For question 2 part 3, here's the solution. I'll try to show a breakdown of the triangles that we're considering. Here's the first triangle, which relates to this triangle here, of course. And here's the second triangle, relates to this triangle here. So basically to calculate the adjacent side of this orange triangle here, it will be 4 meters minus x, calculated above. And to calculate the opposite side of the orange triangle, it will be 3 meters plus y. Hope the diagrams help illustrate the solution here. Question 2 part 4, we've now got to calculate the value of m in the case when y is equal to 0. So this dimension here is equal to 0. So essentially we have this free body diagram on the right hand side where this line is actually this line that's horizontal. So horizontal force here. We've got to calculate the value of m here. Don't forget that this cable here will be subject to the force of mg. I'll just call this F1 in the diagram on the right hand side. I'll show you the full work solution on the following slide. Here's question 2, part 4, solution. Let you review the solution at your own pace. It's actually a simpler solution than that I've shown in the actual lecture. I actually considered 2 equations, analysed summation of horizontal forces first and vertical forces second. But if I analysed it with the vertical forces first, it's a direct solution. So what I'm showing here is a preferred solution. So question 3 relates to heat transfer, double Q, through a surface of a wall of thickness S meters, and it's made from a material which has the thermal conductivity K, watts per meter degree C. So here's the formula. Q is equal to K divided by S. and that's multiplied by D. And D is basically the change in temperature. D is T1, the higher temperature, minus T2, the lower temperature. So heat energy is moving from left to right in this particular instance. For all these questions, temperature T1 is always greater than temperature T2. So question 3, part 1. A solid wall has a thickness of 0.1 meters, is made from brick, which has a K of 0.4. The temperature on one side of the wall is 24 degrees C and on the other is 12 degrees C. We've got to calculate the heat transfer through the surface of the wall. So essentially we'll be inserting the values into this equation. Full solution shown on the following slide. So question 3, part 1. Here's the full solution. I'll let you review this at your own pace. Just a question of inserting the values into the formula. Notice that symbol D, temperature difference, is always T1 minus T2. Gives 12 degrees C in this case. Question 3, part 2. We're given another wall of the same brick with a thickness of 0.1 meters, has a heat transfer of 80 watts per meter squared. We're given the temperature on the cooler side of the wall is 10 degrees C, that will be T2. In this case, we've got to calculate the temperature on the other side of the wall, T1. Hint in the question shown here and the full work solution shown on the following slide. Question 3, part 2, here's the full work solution. Basically involves some transposition of the equation, so I'll let you review at your own pace. Final temperature for T1, 30 degrees C. Question 3, continued. Now we're considering a wall that has N layers. So this is sometimes referred to as a composite wall, such as an insulated cavity wall. But this time the heat transfer Q is calculated by the formula shown here of Q is equal to D, the temperature difference, divided by the summation of the S divided by K. Question 3, part 3. This is part A here. I'll let you read the question at your own pace. We essentially have a 3-section wall. We have breeze block, foam and brick. We do not know the K value for the breeze block or the foam, but we do for the brick. The question wants us to show this formula using the formula for heat transfer through a composite wall shown below. I'll show you the full work solution on the following slide. So question 3, part 3, part A, here's the full solution. Initially extracted the information from the question. Here's the equation given for Q in the question, and I've just written Q in terms of the breeze block, S upon K, the foam, S upon K, and the brick, S upon K. All I've done next is insert the values and rearrange the equation. So I'll let you review this at your own pace. It's basically transposition here. That generates this equation which we're asked to show, which I've labelled as equation 1. Question 3, part 3, part B here. Very similar exercise to that shown in part A. This time we're asked to show this equation given the information in the question. If you follow part A, you should be able to attempt part B. I'll show you the full work solution on the following slide. Question 3, part B. Here's the full work solution. I'll let you review the solution at your own pace. And here's the final equation, called equation 2 this time, that we're asked to prove. And question 3, part C, we're now asked to calculate the thermal conductivity values, the K values for the breeze block and for the foam. So essentially we're going to solve these two equations derived on the previous slides simultaneously. Full work solution shown on the following slide. So question 3, part C, here we're solving for the KB and KF. KF shown here, KB shown here. Essentially just solution of simultaneous equations. I've used the elimination method here. I'll let you review the solution at your own pace. Let's consider question 4. It relates to a car on a test track. It accelerates from rest for 10 seconds when it reaches its maximum speed. After that time, the car continues with diminished speed due to reduced engine power. The speed of the car, v meters per second, during the first 30 seconds of motion is modelled by the formula shown here. V is equal to 12 multiplied by t multiplied by e to the negative t upon 10. T is measured in seconds. On the grid below, we have to draw the graph of velocity against time from 0 to 30 seconds. So obviously we'll need to use the equation and work out some points to help plot the graph. So this is part 1, and I'll show you the solution on the following slide. So question 4, part 1, just undertaking a typical example calculation here. This is when t is equal to 15 seconds, so just simply inserting the value of 15 for t in the above equation, we can calculate velocity at this point in time, and we should do this for further points to allow us to draw the graph, which will not be a linear graph. Full solution shown on the following slide. Here's question 4, part 1. Further values calculated in a table at the top of the slide and the graph sketched as shown. Question 4, part 2. Essentially here we've got to use integration because we're given the speed in terms of v as a function of time t. So to find the distance travelled in the time taken, distance is s, we have to integrate the velocity equation. So to find distance is the integral of our velocity equation as a function of t with respect to t between the limits of t0 and t1. And using the integration, we've got to show the distance the car travels in 30 seconds is shown here in terms of meters. So the hint in the question is it's integration by parts, because this is a product. We have 12 multiplied by t, so obviously that's a function of t, and that's multiplied by e to the negative t upon 10, so that's another function of t, so that's a product. For reference, here's an extract from the formula sheet showing the integration by parts formula. For your further reference, the formula we use in our notes is slightly condensed, it's at the bottom of the slide here, as essentially we cancel these terms. So on the left hand side we have the integral of u dv, shown here, and on the right hand side we have uv minus the integral of v du. So the line at the bottom of the slide is the formula we used in our notes, but this line above here is what's stated actually in the formula sheet. Essentially the same formula, written in a different format. I would encourage you to attempt this question because it's very useful to practice the integration by parts approach, but the full work solution is shown on the following slide. So question 4, part 2, here's the solution using the integration by parts formula. So we have to let one term is equal to u is t in this case, and the other term is equal to dv, that's e to the negative 0.1t. Just notice I've written this negative 0.1t, it's actually negative t divided by 10, that's the same as negative 0.1t. And we will need to differentiate u with respect to t, shown here, and we need to integrate dv to find the value of v, shown here. Here's the solution. Again, I've laboured the solution to try and show you all the steps involved, so I hope that's of some use to you. But this is the expression for distance we were trying to determine. Here's question 5. I'm going to let you review this completely at your own pace. It's actually very similar to a question we analysed in the lecture. I just actually changed the numbers of the vectors. So I'm essentially just showing you the slide here. You should have this almost exact solution in your notes. So question 5 part 1 here. Question 5 part 1 solution. We have to write the vectors OA and OB from the information given in the question. Just added the diagram from the previous slides for clarity. Question 5 part 2. We have to calculate a vector product here. Solution shown on the following slide. So question 5 part 2, here's the solution. I'll let you work through it at your own pace. As I said, we've covered this in the actual lecture. Question 5, part 3. We're informed that the magnitude of vector OA crossed with vector OB is twice the area of the plate OAB. So we've got to calculate the area of the plate. Again, full-work solution shown on the following slide. Question 5, part 3. Here's the solution to calculate the area. Question 5, part 4. We've got to calculate the angle AOB. So this angle in here, effectively, which we can see is an acute angle from the diagram. Full-work solution shown on the following slide. Question 5, part 4. As I said, the solution in this case will be the acute angle. That's by inspection of the vector diagram given in the question. So theta is 40.8 degrees. Just another slide showing the same calculation but highlighting the angles acute. Here's question 6. I'm going to let you review this question totally at your own pace. The electrical context here. So you can read the introduction to the question, note the formulae given and the values given. Question 6, part 1, you have to calculate the value of L. And here's the formula we'll be using to transpose to find the value of L. Question 6, part 1, solution. Let you review this at your own pace. Basically a transposition of the equation. Just noting this solution, I transposed the equation algebraically to find L and then inserted the values given, as shown here. But if you wanted to, you could insert the numerical values from the first line and transpose from there. The final answer for L would of course be the same. Question 6, part 2, how to calculate the value of theta in radians. Shown the extract of the information from the question. Show you the solution on the following slide. Question 6, part 2, here's the solution. Just note the term arctan is the same as tan to the negative 1. I prefer the use of arctan. It saves any confusion between reciprocal and inverse functions. Question 6, part 3. Let you review the solution at your own pace. We haven't really covered all the background work for this particular question, as it refers to the use of some standard compound angle formulae, but nevertheless I'll show you the full solution on the following slide. Question 6, part 3, here's the full solution. So that uses a compound angle formula. And I've tried to label the solution, that helps you. For question 6, part 4, we've got to calculate the average power consumed by the coil here. So we're given a formula for the power in terms of this integral, given the formula for periodic time, it's 1 upon the frequency here. I've got to calculate P. The hint is this requires integration using substitution. Full solution shown on the following slide. Question 6, part 4, let you review the solution at your own pace. We're calculating the average power here. As I said, we're going to solve by using the substitution process. I've labelled the solution somewhat here. And question 7, again I'll let you review this totally at your own pace. First part of the question involves differentiation. I'll let you review the question at your own pace. Question 7, part 1, is the solution. Basically solving this differential equation. It's variable separable. We can get all the h terms on one side and the t terms on the other. And we integrate to find a general solution, a constant k. And we're given the initial condition in the question, t is equal to 0, h is equal to 0.75 meters. So we can insert these values into the above equation. And we can solve for constant k. Constant k calculated here. And then we can exponentialize both sides of the equation to ultimately find height h, shown here. Question 7, part 2. We've got to now use the equation calculated in part 1 to calculate the time at which h is equal to 0.3. For solution shown on the following slide. Question 7, part 2. Here's the solution. So we're solving for the value of t, calculated here. Question 7, part 3. I'll let you review the question at your own pace. When it refers to calculating the maximum height reached by the water in the second tank here, that usually means we have to differentiate and then find a turning point. I'll show you the full work solution on the following slide. Question 7, part 3. Here's the full solution. So we're going to differentiate height h here, find ds by dh, equate it to 0 to find a turning point. Again, a very laboured solution here. Once we find the time for the maximum height, we can then find the distance travelled. Bottom of the slide here. So again, very laboured solution. Obviously, you don't need to lay your solutions out anywhere near as detailed as this, but I'm just trying to hopefully help you in understanding the various steps I've used in generating the solution. Hopefully, I've not made any mistakes in the solution myself. So that's the end of the January 2023 paper, and as always, I wish you well with the impending exam.